Okay, so this is the second part of the set theory videos. I'm going to pick up where we left off in the last video. So we just talked about unions and intersections. The next thing we need to cover is the universe. And probability of the universe is going to be represented by omega. So you can think of this as like the set of everything. Of course, we don't mean the set of everything, it's within context, I guess you could say in context. So if we flip a coin, we might have omega is just equal to heads and tails, because that's every outcome. So this is what I mean by the set of everything. I don't mean it includes everything, but it includes all the everything relevant, or everything within the context. So if we're flipping a coin, everything relevant are heads and tails. Say we roll a die. So then omega is going to equal 1, 2, 3, 4, 5, and 6. So that would be everything in our universe if we're considering rolling a die. So what is the outcome? These are the possible outcomes. Okay, so whenever we get into a specific context, omega is going to be everything that we care about. Part of why we need this definition of a universe is because we want to sometimes talk about things that are not in a set. So say that we take this example of omega. So we'll have roll of a die. And maybe we'll say that A is equal to the set 1, 4, 6. And now then we want to talk about what's called A complement. And we'll say, is everything not an A? And again here, we're a little loose with terminology. So what do we mean by everything not an A? Well, I see the symbols, the numbers 1, 4, and 6 are in A. Well, I'm not 1, 4, or 6. So therefore, I'm not an A. Likewise, this marker is not an A, and you are not an A. But whenever we talk about the complement, we don't want to be quite so ridiculous. It would be hard to talk about much of anything meaningfully. So whenever we say things not in A, we mean in the universe. So the universe is only the numbers 1 through 6. So everything not in A really means everything in the universe not in A. So what's that? Well, 2, 3, and 5 are things in the universe that aren't in A. So likewise, if we say B is equal to maybe the set 1 and 6, B complement will be everything within our universe, but that's not in the set, so that would be the set 2, 3, 4, 5. So that's what we mean by complement, is just everything in the universe outside of the set. Another way to think about this is the set difference. So B complement, sometimes we write it as like omega minus B. And you can think of the set difference of A minus B is the set of elements in A that are not in B. So if we wanted to represent this in symbols, A minus B is the set of X in A with the rule such that X is not in B. So complement's just a special type of difference where we take the entire universe and throw out our set. It turns out always too that once we've defined complement this way, A minus B is the same thing as A and B complement. So the things in A and are not in B. So this is just a rule. It's always equal. If we go back to our example, what would A minus B be in this case? So if we take A minus B, Well, we take A, stuff that is in A, but not in B. So 1 is in A, and 1 is in B, so we don't count 1, because it's only things in A that are not in B. 4 is in A, 4 is not in B. Well, that satisfies the rule, so we would count 4. And 6 is in A, but 6 is also in B, so that doesn't satisfy the rule. And maybe I will add an extra element in B, just to change things up a little bit. So let's say that 5 is in B. Okay, so what happens now? Well, we don't have to put down some kind of -5 or something that's not including 5. So there is no 5 in A, and we're trying to do A minus B. But this works a little different than numbers. We're not talking about numbers, these are sets. So the rule is things that are in A but are not in B. Well, 5 is not in A, so we wouldn't count it anyway. So actually, it doesn't change the difference at all to include some more things in B. Unless we were, of course, to include 4, because then that would cancel the 4 out. Okay. So there are a few special sets that we make up symbols just for those sets. And we'll use them here and there. I mean, they're going to be used in your math classes from here on out, since you guys are hitting the junior level. So we have these blackboard symbols. This just stands for real numbers. And you'll talk about these a little more in your real analysis class. But essentially it means anything on the real number line. We have the integers. Remember, this is the set 0, 1, -1, 2, -2, 3, -3, and so on forever. We have the natural numbers. Which we take in my classes to be 1, 2, 3, and so on. So just the usual counting numbers, or the natural numbers. This is what you learn as a kid as you start counting. Right? And then we have rationals, which basically means fractions of whole numbers. Right? So this is like the set, we call it like P over Q, such that P is an integer, Q is an integer, and Q is not 0. So that's the rule they have to satisfy. So they have to be some kind of integer, some whole numbers. So remember things like 1 over 17 or -2 over 3 are in Q, but square root of 2 is not in Q. Because there's no way to represent square root of 2 as a whole number divided by a whole number. But square root 2 would be in the real numbers. So these are going to be the important ones for this class. Of course, there's the complex numbers, but I don't think the complex numbers will come up too often in this class. Let's see, probably the only other real important topic that I should hit on is the cross product. So if you have a set A and a set B, so A, B are sets, these sets A cross B is the set of tuples. So it's just pairs A comma B, such that A is an element of the set A and B is an element of the set B. So let me run through a quick example of that. Say that A is equal to A comma B. Oh, maybe I shouldn't use these symbols. Let me say it's like 1, 2, and B is going to be 1, 3, 5. Then A cross B are going to be pairs where the first thing in the pair has to be something from A. So 1, and then the second thing in the pair could be from B. So 1 is also in B, we could put 1, 1. And then we would have 1, 3, and 1, 5. So this takes everything with the first elements in A paired with B. And then we would have 2, 1, 2, 3, and 2, 5. And now that we've listed every element in the set, we can close it off. And we do this sometimes also with the familiar sets, so like R cross R, which is just R squared, are just pairs x comma y, such that x is a real number and y is a real number. And this is your familiar, you can write this in the Cartesian coordinate system. Right, here's our real number line for the x's, and here's our real number line for the y's. And then we end up getting a plane of points. Okay, and finally we have functions. So remember that f goes from A to B. Right, this is our domain, this is our range, and this is the name of the function. Okay, so for example, I can say like f goes from R to R by f of x equals x squared. Right, so you put in a real number, it spits out a real number. If we had something like A is equal to the set AB, and B is equal to the set X, Y, Z, we can define f going from A to B by, well, in this case we could just list it out. So this gives us a rule. For every x you put in, you get x squared out. Here we don't have to make up a rule, we can just say what f of A and f of B are. So maybe f of A equals x and f of B equals z. So whenever you plug in these two elements, you know exactly what you're getting out.